The last class we started looking at root locus. We said root locus is nothing but what? Root locus is nothing but how the roots of the characteristic equations are going to vary when Kc varies from 0 to infinity, isn't it? So how the roots are going to vary in a complex plane, how the roots of the characteristic equations are going to vary in the complex plane where the controller gain Kc varies from 0 to infinity, isn't it? So this entire locus of the root we are calling it as a root. Why it is important? It is important because not only it gives you a information about the stability of the control system, but also it gives you a information about what type of response you are going to get. Whether it is exponential type of response, whether it is oscillatory type of response, all that information you get based on the location of the root. Also you get additional information which is what value of Kc is going to make your system stable. Isn't it? What value of Kc is going to make your system stable, and very often people use a conservative value of Kc. Why? Because if you use a higher value of Kc, then your system response is faster, but there you may end up with having a unstable response. Isn't it? So you wanted to operate as much as away from the region of instability, isn't it? So how much margin you are having from the range, how much margin you are having from the region of instability, that is also important, isn't it? There is something called as a gain margin and phase margin. That when we start looking at the frequency response, maybe in the next class onward, we are going to look at frequency response. There we look at the concept like gain margin and phase margin, which actually defines how much is the tolerance in your system for stability. Remember, in this case, the entire stability depends on the value of Kc, tau I, Kc, tau, tau m, tau f, etc. Isn't it? Which are nothing but the parameters associated with the system. Correct? Very often the system is poorly understood. In such cases, working with a fixed value of tau or working with a fixed value of Km, Kp, etc. can lead to a unstable operation. Then there is some tolerance. You might have got some value, maybe tau equals to 3 experimentally. But experimental value may have some fluctuations. That means this value 3 is not the exact 3. Isn't it? It could be 3.2, it could be 3.5 also. Isn't it? So you have to design your control system in a robust manner in such a way that even though there is a fluctuation in this value, still your system is stable. Isn't it? So clearly you wanted to know how far you are from the region of instability. Clear? So all this information you can get from the flow. Okay. So in the last class we started looking at the how we can plot a root locus. Isn't it? There are different rules given by Evans. Clearly finding the root locus directly from the characteristic equation and solving and finding the roots is not going to be possible. भैया क्या हो गया, ध्यान दे दो आगे, ये थोड़ा मुश्किल है टॉपिक, ठीक है? अदरवाइज मुझे आना पड़ेगा फिर हॉस्टल में तुम्हें समझाने के लिए. यहाँ नहीं समझोगे तो कहाँ समझोगे? ऐसा कुछ है? ये लैपटॉप बंद कर दो भाई, क्यों ओपन कर रहा है? लैपटॉप में कुछ नया चीज समझ आ रहा है? कुछ नया समझ में आ रहा होगा तो बता दो. Please switch off your mobiles and laptop and please pay attention. Okay? Whatever I am doing in my slides or whatever is there in your book is not going to come exactly. Something other than this will come. So you better pay attention. Okay? Okay. So there are 6 rules given by Evans. Okay? These rules are actually enabling you solving the root locus easily without finding the exact roots of the characteristic equation. Remember, we said if the characteristic equation is having a order more than 3, finding the roots is not going to be easy. Correct? And which is going to happen regularly in a chemical processes. Let's say if if you are having a distillation column, how many trays we have? 25 trays means the order will be 25. So what will be the order of S in a characteristic equation? 25. Will you be able to solve? It is not possible to solve. Correct. So you need to have a procedure which enables you drawing the entire root locus without finding the exact roots of the characteristic equation. And there this methodology given by Evans is extremely important. Why? Because you can draw the root locus, at least rough sketch of the root locus you can draw without finding the roots. Without finding the roots. Okay. So what are the rules? Rule number 1. Rule number 1 says number of loci or branches is equal to the number of open loop poles. So whenever you have a transfer function, you can find out the open loop poles directly, isn't it? For instance, let's say if you are having this particular transfer function you are having, you can easily find out what are the open loop poles and zeros. Isn't it? Open loop poles in this case will be what? Minus 1.45, minus 2.85 and minus 4.35. These are the open loop poles. Similarly, you can find out open loop zeros. Open loop 0 will be minus 2.25. Isn't it? So rule number 1 says the number of loci or branches will be equal to the number of open loop poles. So first step is to find out how many open loop poles are there. What is open loop poles and why we are calling them as open loop poles? These are the roots of the characteristic equation when Kc is 0. When Kc is 0 means controller is not a part of a feedback control system. So what it means? Loop is opened just after the controller. So that is why we are calling them as a open loop poles. Okay. So the first step is number of loci or branches is equal to the number of open loop poles, let's say n. That is rule number 1. Okay. So these many branches are going to stop. Then rule number 2 says the loci begin at the open loop poles and terminate at open loop 0. Remember, we can find out open loop poles and zeros easily just by looking at the transfer function, isn't it? So what we are saying in rule number 2 is the branches which started from open loop poles, some of these branches are going to get terminated at open loop 0. And remember, I said several times, for all practical purposes, the number of poles are going to be more than number of zeros. That means what? Only some of the branches which started from open loop poles will get terminated at open loop 0. There will be remaining, isn't it? Let's say there are m number of zeros. So that means only m number of branches are going to get terminated at m number of zeros. So there will be remaining m minus m branches which do not have a place to get terminated. Isn't it? Remember, in this case, n number of branches are going to start because there are n number of open loop poles. But there are m number of zeros. So out of this n, only m branches will get terminated at m0. So there will be remaining n minus m branches which do not have a place to terminate. And all these n minus m branches continue as asymptotes. Okay, that is what is written. So in this case, the termination of n minus m loci will occur at zeros and infinity. So remember, this remaining n minus m branches which do not have a place to terminate at 0, they will continue as asymptote and they will terminate at infinite. They will terminate at infinite. Okay. Again, while applying this rule, remember, in some cases we have poles which are multiple poles. That means there are 2 roots present at one location or 3 roots present at one location. So whenever we have a multiple poles, then multiple loci emerge from that. Similarly, if we are having a multiple 0, so multiple 0 means multiple loci are going to get terminated at that multiple 0. Okay. So qth order poles should be counted q times. Similarly, qth order 0 should be counted q times. Okay. Is it clear? Again, if you are having the complex conjugate root, then in that case, In that case, what will happen? Can we have a complex poles? Can we have a complex poles? We can. So in that case, the root locus will start from that complex. Similar cases we have not done here, but you can have even the root locus started from the complex pole. Okay, all right. Now look at rule number 3. This is a very important rule. Rule number 3 says real axis becomes the part of a root locus. What you have to do is you take any point on a real axis and see if there are number of poles and number of zeros. If you count their numbers, if their counting becomes odd number on the right hand side of that particular point, in that case that particular point is a part of a root. Okay, that is what it is written. So real axis is a part of a root locus when the sum of the number of poles and zeros to the right of the point on the real axis is the odd number. Okay, we will see this particular rule again in the context of one simple example, then you will appreciate it more. Those who have done the tutorial, they probably able to appreciate now, isn't it? It is necessary to consider only the real poles and zeros in applying this rule, because whenever you have a complex poles and complex zero, doesn't matter because they always occur in a conjugate pair. So it cancels out, isn't it? So you don't need to count there. Even if you are counting, doesn't matter. Anyway, these are going to happen in pairs. Furthermore, the qth order pole must be counted q times by applying this rule. Alright. The next rule is rule number 4. Remember, in this case we say if there are n number of poles, in that case n number of loci are going to start, isn't it? And let's say if there are m number of zeros, in that case only m number of loci get terminated at m zeros, remaining n minus m. Remaining n minus m loci will continue like asymptote and they will get terminated at infinity, isn't it? So number of asymptotes will be equal to what? Number of asymptotes in this case will be equal to n minus m, where n is the number of open loop poles and m is the number of open loop zeros. Okay. So there are n minus m loci that approaches as k tends to infinity asymptotically, n minus m straight lines radiating from the center of gravity of poles and zeros, and all these asymptotes radiate from the center of gravity, and you can calculate center of gravity as summation of pi minus summation of z, summation of pj minus summation of z divided by n minus m. And each of these asymptotes is going to make an angle with a real axis, isn't it? And the angle these asymptotes are going to make is pi into 2k plus 1 divided by n minus m. So you can see that each of these asymptotes make an angle of 2 pi divided by n minus m with respect to each other. With respect to each other. And this information is extremely important. Why? Because you can draw a rough scale based on this information. You can first obtain the center of gravity, and once you get the center of gravity and once you get the angle, you can draw a straight line from the center of gravity. These straight lines which are drawn at a given angle will be the direction of your angle. So you can get a rough scale of root locus directly from this information. I am saying rough scale. Remember, this word radiant is very, very important. This radiant, what it means is, if you draw a straight line, you will connect it to this. But it doesn't mean that the root locus will start from center of gravity. It only says radiate from that point. It doesn't mean that it is starting from that point. That is why radiate word is used here. Okay. Alright. So in this particular equation, when you are calculating the angle, the k will be varying as 0, 1, 2, 3 all the way to n minus m plus 1. Correct? Sorry, n minus m minus 1. So it is starting from 0. So total number of asymptotes are n minus m, and since it is starting from 0, the counter will be n minus m minus 1. Okay. Alright. Then rule number 5. Breakaway and breaking point. So So very often what happens is the root locus is started from the open loop pole, isn't it? And then the root locus move towards each other. These roots meet at a common point and then they break up. Similarly, if there are open loop zeros are there, in that case what happens is these root loci meet each other on a real axis and then move towards the zero. So both these points are referred as breakaway or breaking. How you can calculate the location of this breakaway and breaking point? Breakaway and breaking point you can obtain by solving the equation. Summation of 1 upon s minus pj should be equal to summation of 1 upon s minus j. If you solve this particular equation, you will get the location of breakaway and breaking point. So once you get this breakaway and breaking point, the actual root locus makes an angle of plus or minus pi by 2 at this breakaway and breaking point. Okay, remember this. The root locus makes an angle of plus or minus pi by 2 at breakaway and breaking points. Okay, that is what is given here. Alright. So once you obtain the breakaway and breaking, then you can draw a rough sketch. You can draw a rough sketch, and in between points you can obtain by using angle criteria and magnitude criteria. Remember angle criteria and magnitude criteria we have discussed in the last class. Isn't it? You can select any point in this rough sketch, find out its angle with the open loop poles and open loop zeros, and then its angle with open loop zeros minus its angle with open loop poles, that will be equal to odd multiple of pi. Isn't it? If this particular criteria is satisfied, it's an angle criteria. Once a particular point is satisfying the angle criteria, it means that that particular point is a part of the equation. Once you find out a point is satisfying the angle criteria, then corresponding to that point you calculate what is the distance of that point from the open loop poles and open loop zeros, and you can calculate what is the magnitude of K corresponding to that. Isn't it? So this particular equation is referred as magnitude criteria. That is what we have seen earlier. This is what we have seen, is the angle criteria. Isn't it? Once you satisfy the angle criteria, then you put all these distances here in this equation and you can calculate K, which is a magnitude criteria. Isn't it? Okay. Now the last rule is, remember if you are having multiple poles or multiple zeros, at multiple poles or multiple zeros there will be, let's say if you are having qth order pole, then q loci will be starting from that point. Isn't it? But this q loci, this will move from this real axis with an angle. They are not going to move directly on a real axis. They will be inclined. What angle these loci are going to make with the real axis, that is something called as angle of departure or angle of approach. So from loci, these loci are going to make an angle of departure with the real axis. And similarly, if you are having the V's order 0, in that case, the loci are going to terminate, but they are going to terminate with an angle. Isn't it? And that angle will be called as angle of approach. Okay. So angle of departure and angle of approach you can calculate by using this equation. So you can see this equation is actually modified form of this equation. This is the modified form of this. So see, theta in this case, which is nothing but the angle of departure from for all q loci which are emerging from the qth order open loop pole PA. So that is given as 1 by q 2k plus 1 pi plus this pole is making angle with all zeros. So you are summing up that angle with all zeros, isn't it? Similarly, you are subtracting how much angle this pole PA is making with respect to the remaining poles. Okay, and that you are subtracting. So this particular theta is going to give you the angle a particular qth order loci are going to make with the real axis. Okay. Similarly, if there is a weak order 0, in that case you can find the angle of approach which is given by 1 by v, 2k plus 1 pi in this case, slightly different equation is there. So in this case, you are having a 0. So you are finding out the angle of this particular 0 with respect to all the poles minus then what are the angles this 0 is making with respect to the remaining 0. Okay. I remember I have given one of such questions earlier. Okay. And nobody able to do it. So please pay attention. This is not straightforward. This is not straightforward. You will not find even a single example solved on this in the book. Okay. So don't come later on, there is no example solved. That is why I am explaining again and again. This angle of approach and angle of departure is very, very important, because in a usual case, remember in this case we are talking about qth order pole and nth order zero. But in a normal case, if you are having a normal pole or normal zero, what angle it makes? It's a real axis. What angle it makes? It's a real axis. It is either 0 or phi. It is either 0 or phi. Isn't it? But this angle differs only in case you are having a multiple poles or multiple sides. Not straightforward. Okay. So that is what is written here. So simple poles or zeros will make the angle of 0 or phi. Another thumb rule while drawing the root locus, another thumb rule is you can consider poles as a positive charge, you can consider zeros as a negative charge. So whenever the poles are there, loci emerging from poles, they will repel each other, isn't it? So you can see that again root locus is symmetric. Root locus is symmetric. Whatever is the symmetry at the upper half, the same will be at the lower half. So these are the common things. If you remember, you will be able to draw a root locus without any trouble. Okay. Alright? Let's look at example. Then you will understand all these rules. Now in this particular case, let's say the transfer function of the process is given as k divided by s plus 1, s plus 2, s plus 3. Again, for a simplicity, we are assuming that the final control element and measurement unit there. Maybe you can consider that there is a second order process, but one of these s plus 3 is from the, let's say, measurement unit. Okay. Let's say this is the open loop transfer function G, for a simplicity. Open loop transfer function G, which has the impact of all process as well as controller as well as final control element. Remember what is G? G is nothing but GP, GC, GF, GM. Isn't it? So all this is included in this G. Okay. Now what will be the open loop poles here? Open loop poles are -1, -2, -3. Isn't it? So first I am going to identify the open loop poles -1, -2, -3. Isn't it? Rule number 1 says the number of open loop poles, whatever the number of the open loop poles is there, that many number of loci will start. Isn't it? That many number of branches are going to start. So in this case, there are 3 open loop poles, 3 branches are going to start, and they are going to start at location -1, -2, -3. So let me locate these open loop poles here. So you can see this is -1, this is -2, and this is -3. So 3 loci are going to start at this 3 poles. Then rule number 3 says a root locus, the real axis becomes the part of a root locus where the total number of poles and the zeros on the right hand side on the real axis becomes a odd number. Isn't it? So let's take any point here. Any point. How many poles and zeros are there on the right hand side? 0. 0 is the even number. So that is why this particular part of a real axis is not a part of a root locus. Now consider any point here in between. How many poles and zeros are there on the right hand side? 1. So that is why between this -2 and -1, this real axis becomes the part of a root locus. Why? Because the sum of the poles and the zeros, their number is the odd number here. Okay. Again, take any point here. How many poles and zeros are there on the right hand side? There is 1 pole here, second pole here. So number of poles are 2, which is a even number. So clearly, this part of a real axis is not a part of a real axis. Isn't it? You can take any point here, any point on this entire arm. How many poles and zeros are there on the right hand side? 3. So therefore, this particular R is going to be a part of the result. Okay. Now, what is rule number 4? How many asymptotes are there? Number of asymptotes in this case will be n minus n. What is the value of n? 3. M 0. Isn't it? So 3 minus 0, 3. How many asymptotes we are expected to get? 3. And all these asymptotes are going to terminate at infinite. Isn't it? Remember again we said that all these asymptotes are going to radiate from the center of gravity. Isn't it? So what will be the center of gravity? Center of gravity is summation of Pj minus summation of Zi divided by n minus n. Isn't it? So we can calculate the center of gravity. So center of gravity is minus 3 minus 2 minus 1 divided by 3. So that comes out to be minus 2. So clearly this minus 2 point here is the center of gravity. Isn't it? That's the center of gravity. No, it will. Why? Because if you are having, let's say, any conjugate, that will cancel out. It will. It will be only on the real axis. Another important thing, all these rules, do you think these are empirical rules? These are not empirical rules. You can prove all these rules from this equation. You can prove all these rules from this equation. And that was also one of the questions I have given. Okay. So you can prove all the rules from this equation. It's not coming from heaven. There is some logic. Okay. For instance, let's say if I have this, if you are having, let's say, a positive feedback system, 1 minus DOLTF will be equal to 0. In that case, all the rules are going to change. Instead of odd number, in that case it will be even number. Okay. So these rules are not coming, these are not empirical rules. These rules are actually coming from this equation and you can prove. Okay, let's move to the next point. So once we have obtained the center of gravity which is minus 2, which is this particular point. So clearly, all my loci, all my asymptotes should be radiating from this point. Radiating from it. I am saying radiating. Okay. Then we have to find out at what angle these asymptotes I am going to have. So the angle in this case will be given by 2k plus 1 into pi divided by n minus n. And k is value as 0, 1, 2. Isn't it? So if I put that, I am going to get the angle which comes out to be pi by 3, 3 by 3 and pi by 3. So you can see that I can draw the asymptote. This is one asymptote which is making an angle of pi by 3 with the real axis. This particular asymptote which is making an angle of pi by 3, and this particular arm will also another asymptote which is making an angle of pi. And all three asymptotes are actually radiating from this point. You can see this particular asymptote is not connected here. This root locus is not connected here. There is a dotted line here. Okay. Again, one more thing to note down. Asymptote doesn't mean that asymptote is a root locus. Asymptote is not a root locus. Root locus is going to follow the asymptote. Draw the asymptote first, and then you can draw the root locus which will be following the asymptote. So asymptote means the root locus is going to follow these asymptotic lines when k becomes very large. Okay. That's why the word this asymptote is used. Your root locus is going to follow these lines only when k becomes very large. Okay, alright. So now, once we have obtained this particular graph, now only the real axis we have shown as a root locus. Now what is happening here? One of the loci is going to start here and continue as asymptote, and the two more loci are going to start here and here. Isn't it? There is no space going, isn't it? That means they will move towards each other. They will meet at a common point and then they will break up. Isn't it? So you have to find out the breakaway point in between. That's the only possibility we have. So in this case, we can find out the breakaway. So breakaway, the equation is summation of 1 upon S minus Pj should be equal to summation of 1 upon S minus Zi. Now here 0 is not there. So right hand side is 0. Only the left hand side 1 minus 1 upon S minus P Pi will be there. So 1 upon S plus 1, 1 plus 1 upon S plus 2 plus 1 upon S plus 3 should be equal to 0. If you solve this particular equation by using trial and error, you get the breakaway point which is 1.42 minus 1.1. Once you get this breakaway point minus 1.42, that is this point. This is the breakaway point. So our root locus will follow what? It will start from this point. Another root locus will start from this point. They will meet at this common point here, and then they will break up. And remember, in the breakaway point, the angle the root locus makes with the real axis is plus or minus 5 by 2. So you can see that this entire root locus is making an angle of pi by 2 here, plus or minus 5 by 2. And then, as the value of Kc increases, it follows the axis. So my real root locus is shown by a red line. Please note that my real root locus is shown by a red line. This dotted line is not a root locus. This dotted line is a asymptote. The root locus is going to follow the asymptote when k becomes large. Okay. Don't consider this dotted line as a root locus. No, these are not a root locus. Okay, is it clear to everyone? भैया कहाँ ध्यान है मोबाइल में घुसे हो? Remember I said I ignored first time. Second time I try to pick up. कहाँ हो भैया? यहाँ हो? ध्यान दे दो, ये समझ में नहीं आएगा, ये थोड़ा सा बाउंडर है, ये समझ में नहीं आएगा। बोलिए ऐसे क्या ऐसा आएगा ही, तो कुछ और ही आएगा, तो बेटर है अभी से ध्यान दे, ठीक है? Where we are? So once we get this breakaway point, then we can draw the root locus. Note that here the arrows are extremely important. Arrows are extremely important. Remember, in the last graph, I have shown only one arrow here. Why? Because I am only certain about this particular arm. This particular arm is going to the infinite. It's a asymptote. It is going to follow the asymptote. So that's why only one arrow I have shown, but I have not shown any arrow here. Once I get a breakaway point, then I can show the arrow. One is going towards this, another one is going here. They are meeting at the common point, and then the arrows are outward arrows. So these arrows are important. What these arrows are showing? These arrows are actually giving you the information that what is the direction of increase in Kc. As the value of Kc increases, how your roots are going to vary. This direction is given by arrows. Okay. Now you can see that this root locus is crossing this imaginary axis. So there is some value of Kc at which the roots are located exactly on the imaginary axis. Isn't it? That means the system is marginally stable there. If I increase further the value of Kc, then my system is going to become unstable. So I need to find out what value of Kc corresponds to this point. So how I can find out that? I can use a round stability criteria. Isn't it? What is round stability criteria? I can start with the, remember this is the equation. This is the equation. So 1 plus g should be equal to 0. That is the characteristic equation. Isn't it? So what I am going to get from this? 1 plus g equals to 0. So I am going to get this. Isn't it? S plus 1, S plus 2, S plus 3 plus k equals to 0. This is what I need to get. Isn't it? And once I get this, I can simplify. I will get a polynomial in S. And from this polynomial in S, I can draw the round array. I can make a round array. Isn't it? So this first element is going to be A0. Second element here is going to be 11. Then this will be 6, and the last will be k plus 6. Then after that, all other elements you can calculate. Isn't it? Correct? So 6 into 11 minus 1 into k plus 6 divided by 6 will be thus this third element here, and the last element is going to be k plus 6. So now if you concentrate on all the elements present in the first column, only this third element can become 0 or negative. All other elements will be always positive. Isn't it? that means stability is determined only by this element, isn't it? So for stability, this entire element should be greater than equal to 0. If I equate that, then I will get the value of Kc. So if I put that, I will get the value of Kc, that means K here. The value of K should be less than 60. The value of K should be less than 60. If the value of K is greater than 60, then my system is going to be unstable. And at exactly K value equals to 60, it will be marginally stable. So when K equals to 60, this particular element becomes 0. Then I can find out the location of the roots on the imaginary axis. How? This will be the j row. What will be j minus 1 row? This. So 6 into s square plus k plus 6. So k in that case will be 60. 60 plus 6. So you will get 6s square plus 66 equals to 0. So you will get the location of this crossover points, which comes out to be plus or minus 3.32 iota directly. So we have obtained these points. These points we have. K is all of us. Okay, is it clear to everyone how we have find out these 2 points? Once we have obtained these 2 points, then we know where to work. For instance, if I work the value of K greater than 60, then I am going to have a unstable system. Isn't it? If I have a lower value of K than 60, then I will have a stable system. Is it clear to everyone? Correct? So once we have obtained these points, these 2 points, these breakaway points, then we can roughly draw the root locus. If I wanted to find out some more points here and here, then we can use the angle criteria and magnitude criteria. We can find out different points here. Remember earlier when we started looking at angle criteria and magnitude criteria, what was the problem there? We have to select the point randomly in the complex plane. Now we are not selecting the point randomly. We are selecting the point which is close to this rough sketch. So that assumption of randomness is gone. Remember that angle criteria and magnitude criteria which we started initially, we said will be difficult to implement. Why? Because we have to select a point randomly in the complex plane and we have infinite number of such points. Which point to start with? But now we are getting an intelligent gaze here. Once we draw a rough sketch, now we are getting the intelligent gaze to start with, which will more or less satisfy the angle criteria. Okay. So similar illustration is shown here. You can see if we select a point SC and we can calculate the angle. Whenever the angle is matching it, in this case the angle is not matching 180. So clearly this point is not a part of the root locus. Then I am going to move this point right or left. In this case, if I move a point on the left, in that case these angles are going to increase. Once I move this point on the left, these angles have increased. And now the total is coming out to be 181, which is very close to the odd multiple of 1. So clearly, with this value, if I take a value 0.95 plus 1.5 iota, this particular point is actually a part of the root locus. Whereas this particular point, which is minus 0.75 plus 1.5 iota, is not a part of the root locus. Okay. Once we have found out that this particular point is a part of a root locus, I can calculate what is the value of K at this point. How? I can find out how much distance this SC is having from E1, E2 and Z1. I can take a ruler and measure that distance directly. And that distance will give me the magnitude. And from that magnitude I can calculate what is the corresponding value of K. So in this case the corresponding value of K comes out to be 6.8. Okay. Another interesting thing is, remember from the linear algebra we know that whenever we are having a polynomial, summation of all the roots should be equal to minus a1 by a0. Minus a1 by a0. Let's say you are having a polynomial with degree let's say 3. How many roots are possible? 3 roots are possible. Out of these 3 roots, let's say 1 root is a complex quantity. So that means another root we know. Third root you can directly obtain by applying this. So you can draw a root locus easily if you know the concept. It's not difficult. Without finding the actual root you can do it. Isn't it? Alright? Let's make our life slightly difficult. So this is the same problem. This is the same problem. How this concept is useful in a feedback control system, that is what is shown. Let's say the controller is KC and GP is, let's say, second order process, and this GM is, let's say, again first order process. So in this case tau 1 and tau 2 are taken as. So in this case you can see that if I find out the represent this entire term in a standard form, I can represent this as KC divided by, so see, if I divide this entire equation by tau 1, tau 2, tau 3, isn't it? Then I will have KC by tau 1, tau 2, tau 3 will be K, and I can represent denominator as S minus P1, S minus P2, and S minus P3, where P1 will be minus 1 by tau 1, P2 will be minus 1 by tau 2, and P3 will be minus 1 by tau 1 added. So with this is the same equation we have seen. The root locus is already we have got, isn't it? So you can see that this is kind of illustration that how the feedback system can be mapped into this root locus, and how you can find out the root locus of the feedback system when the KC value is varying from 0 to infinity. Okay, clear? Is it clear to everyone? Let's look at slightly more complex example. So now instead of a proportional controller, now you are using a PI controller. Now you are using a PI controller. So with PI controller, the transfer function is Kc 1 plus 1 upon tau is. Correct? Now what will be the open loop transfer function? Open loop transfer function will be Gc, Gp, Gm. Isn't it? Gc is this Kc into 1 plus 1 upon tau is. I can simplify this to what it will be? Kc into tau is plus 1 divided by tau is. Let's say if we take the tau I equal to 1 by 4. In that case, the open loop transfer function will be given as Kc tau is plus 1 divided by tau is, tau 1 is plus 1, tau 2 is plus 1, and tau 3 is plus 1. And again, if we represent in terms of the previous example, we will have open loop transfer function as K s plus 4 divided by s into s plus 1 into s plus 2 plus s plus 3. Now we are having how many poles? How many open loop poles we are having? 4 open loop poles we are having. One at s equals to 0, another at s equals to minus 1, minus 2, and minus 3. And there is a one open loop 0, which is at s equals to minus 4. Isn't it? So what we have to do again? We have to find out these open loop poles at 0. So see, all the poles are denoted by cross here. So minus 0, minus 1, minus 2, minus 3, and this 0 at minus 4 is shown by a circle. Then you can apply rule number 3. What is rule number 3? The real axis becomes the part of a loop locus when the number of poles and zeros on the right hand side becomes odd number. Isn't it? So if I count the number of poles and zeros here, it is 0. So clearly this particular arm is not a part of a loop locus. Between minus 1 and 0, only one pole is there. So clearly this particular arm will be a part of a loop locus. How about this minus 2 to 1? There are two poles here, so clearly this will not be a part of a loop locus. And between minus 3 and minus 2, minus 3 and minus 2, there are two poles here, isn't it? So 3 poles are there, so this will not be a part of the loop locus. This minus 4 to minus 3 will be again between these 1, 2, 3 are there, isn't it? So this will be a part of a loop locus. So in this case, okay. So between this minus 4 to 3, this will not be a part of a loop locus. Again, this will not be a part of a loop locus. This entire arm will be a part of a loop locus. Correct? So we can identify that. We have identified that. Then we have to find out the center of gravity. Center of gravity, summation of Pj minus summation of zeta divided by n minus n. Again we have obtained center of gravity that comes out with minus 2 by 3. So minus 2 by 3 is this particular point. So from this particular point, all your asymptotes will be radiating. Now how many asymptotes you have? 4 minus 1. in this case, see, this is minus 1, minus 2, minus 3, how much? That will be minus 6. Minus 6 plus 4. Now, minus 2 by 3. Correct. Here there is a minus sign because you are having the 0 and minus 4. So minus of minus will be plus. Correct. So there is a minus sign in here. So answer is minus 2 by 3 is the correct answer. That's a typo because anyway these are made last year, isn't it? I have eliminated several typos, but still there are some typos today. Okay. Anyway, so minus 2 by 3 is this particular point. So from this particular point, E asymptotes will be radiating. And what angle these asymptotes are going to make? Pi by 3, pi and pi by 3. Isn't it? So these are the three asymptotes. So clearly this particular arm will continue as asymptote. One more asymptote is moving here, another is moving here. Then clearly the root loci will be starting from all these four poles. Here, here, here and here. Isn't it? So root loci from here will move towards here. This will move towards each other and they will break up. So how many breakaway points are expected here? There are 2 breakaway points we expect and 1 breaking point. Why? Because these 2 loci will move towards each other and they will follow the activity. How about here? They will move towards each other, they break away and they will meet here. So there is a breaking. There are 2 breakaway and 1 breaking point they are expected. So you are going to get a breakaway point from this equation. So there are 1 breakaway at minus 0.41. So this is the point at which you will get a breakaway. Similarly, the second breakaway point is minus 2.68. So from there here you will get a breakaway. And there is a breaking point which is at minus 4.705. So your root locus will be typically given like this. Okay. Alright. So then we can find out the crossover point. This crossover point we can find out by solving a characteristic equation. So with the characteristic equation you can see that there are 2 k values you are getting. K equals to 60 and k equals to 6.87. 6.84. Sorry, 3.84. So clearly 3.84 is a lower value than 60. So here the limiting value will be 3.84. So with 3.84 this entire term is going to become 0. I can find out what is the location by using the j minus 1 row, and that comes out to be 1.28 iota. So these 2 points will be plus or minus 1.28 iota. So you can draw the entire root locus with this, and you can also find out what is the value of k which is making your entire system unstable. So we will stop here and we will start with the frequency response today. Okay. So we will have an extra class today from 6 to 9, sorry, 7 to 9. 2 attendance we will count.
हाँ बोलने जा रहा हूँ मैं 7:30 से
मैं